All right, ECGR 41, 61, 51, 96, and MEGR 4127, lecture 3. We've already looked at a couple of videos. For those of you looking at this online, I've got a couple of other videos that we'll look at later, or we've already looked at them. Today we're going to have presentations by everybody else, and then continue up on locomotion, and then some lab time if we get that far. So we will go in the order of what it was on the sheet. The person will come up and do their own. I will be sitting right next to the camera and scoring, and I'll hand out the score sheets at the end. Keep in mind, 1 to 2 minutes. 1 to 2 minutes. I'm not going to tell you how long to go. Our first person, go for it.
Are we on the order?
Nope. All right, remember to speak loudly.
Alright, whenever you're ready. Alright. So my presentation today is on different types of gears and what gears do in a mechanical setting. And obviously, they transmit torque. So if you didn't know that, that's what they do. As you can see on the screen, I got a bunch of different types of gears here. The most common is spur gears, which you can see over on my left, your right. And the small gear is called a pinion gear, and then other gear is just called a gear, and it transmits torque through the number of teeth that it has with a ratio. So the torque ratio depends on the number of teeth that each gear has, and you can do that mathematically. Helical gears are pretty much the same as spur gears, except the teeth are on an incline. Worm gears are like this one down in the bottom, and they just move pretty slow. Rack and pinion, everybody has one if you drive a car. That's how your front car is done. And then there's bevel and miter gears as well. So that's just several different types of gears that are used in everyday life. Hit the back button. There you go.
Next. All right. I'll tell you what, to keep in the order of time, what you do is when you're up there and you're done, hit the next, so that we know who the next person is. And by the way, I need to grab my glasses from up there. All right. Next. Who's hydraulics?
I did hydraulics, and they're basically linear actuators that use liquid in order to pressurize a movable piston. The fluid is sent from a hydraulic pump through hoses to the cylinders. On the lower picture there, you can see the hoses that are attached to the actual pistons, and they're actually connected to a hydraulic pump that pressurizes the lower cylinder, and either, well, if it was pressurizing it, it would, raise the ramrod, which is the silver part, forward. It's capable of lifting a high amount of weight. You also have, like pneumatics, which are, air, and that's just not as, strong, and it's able to compress, whereas this uses oil in hydraulics, and the oil cannot be, compressed as easy as air, and so they can lift a lot more weight, and can be used in much, heavier machinery. In this case of, robotics, you have those, like, fight robots that you saw. They used to have a show on it, I think on Comedy Central or something like that.
BattleBots?
Yeah, the BattleBots. Those were probably all hydraulic, you know, because there's a lot of force. Those were like bending metal things. So it's based on Pascal's principle. You know, like both cylinders are equal amount of pressure in it, and that's just mathematically stating that, you know, the force divided by the area is equal to the force on the other cylinder divided by the area if the pressure stays constant, which is a hydraulic system, that's pretty much what you want.
Really similar to hydraulics, but pressurized, pressure by gas instead of liquid. And I mean, pneumatics and hydraulic both can be applied to similar fields, like mining and stuff. Like they try, and usually pneumatics combined with electrical components. For instance, like we say dentistry, they have this chair. It's like they rise it with pneumatics and drop it when they use electrical components. I don't know how it works, but that's how it is. And yeah, the application can be applied to mining, petrochemical industry, defense, entertainment. Yeah, so. It's just really similar to what Darren was doing. Yeah, the one use gas. That's it.
By the way, there's no need to applaud. Everybody will, you know, we'll just assume that everybody's going to be applauded for. The reason I say that is because it's going to slow us down. So.
DC motors. So you have an AC motor and also a DC motor, which a lot of people don't realize. Works on the physical principle of Lorentz force, which if you had Dr. Adams' class or Physics 2, you will know that if you put a current carrying conductor in the presence of a magnetic field, you'll find some force on that conductor. And if you configure your machine cleverly, you can get your motor to rotate around an axle. Basic components of the stator, the rotor armature, the commutator, and the brushes. So as the stator name implies, it's the stationary portion that's a permanent magnet encompassing the outside of the rotor. So that's where you see the blue and the yellow, north-south, the square, that's your stator. The armature rotor is the rotational part that it's kind of, you also have the red and blue, but it's around the axle, so that's actually rotating. Your commutator is the gold portion that's split in half, so this allows the direction of current to alternate. You have to have that in order for the DC motor to work, otherwise there's no rotation. Brushes and or controllers, so if there's two types of motors, you can do a brushed motor or a brushless. A brush motor uses these two contacts that are actually physically in contact with your commutator that allow the current to flow. If it's brushless, you're using a microcontroller to basically impulse current into the commutator. Variants, as I said, brushed or brushless. Homopolar, that's kind of a field all on its own, so I didn't really go into that. But really the key concept to understand is that you have to have some type of commutation in a DC motor. That's basically an electrical switch that periodically reverses the direction of current to allow the rotor to turn. That's all I got.
Any questions? Alrighty, next.
Okay, my concept was on stepper motors. I won't go into the details of the brushless since it was just going into, but it is a brushless electric motor that converts pulses into mechanical shaft rotation. In other words, in this top picture in figure 1, if you, depending on the direction of current flowing through the wires here, will create a magnetic charge, and it will attract obviously opposites, and you can change the current to different spaces or different stators, and you will force the rotor to turn. It utilizes an open loop control system, meaning that there is no feedback as to what position it's in. It's pretty much in the position of wherever the magnetic force is turned on to with the current. It's pretty accurate, normally within a range of 3 to 5%. The more steps there are, as in the first example, it pretty much, as you turn current on from the top, let's say top magnetic field here, and then turn that off and move it to here, it will jump, which creates a bunch of vibration. So the more steps you have in it, the smoother it runs. Micro stepping, as you see here, you'll see the more steps. I'm backtracking, but you'll see the more steps here, so I can move this thing around in smaller degrees with the mini poles on the stator and the rotor. Micro stepping is a way to vary the amount of current instead of just quickly giving it a full current boost, which also makes it basically decrease the vibration from jumping to new positions. Wave stepping is where I'm on full current, off, on full current. I pretty much have one stator magnetically charged at a time, the rest are off. Half step is where I'm back down here on this one, where there's times where I have 2 charged. This one has more torque than the wave stepping as shown here. And then there's micro stepping and full stepping, which always have 2 different poles on at a time.
Any questions?
Next. A servo motor is pretty much just a DC or AC motor that has a built-in encoder, and this enables you to have a negative feedback for position and speed. And the way you get that back from the encoder is it outputs pulses that are counted. And some of these applications include industrial robotics and automation, autonomous robots, automotive and machine tools. And that's it.
Wow.
Next.
Nice.
Next.
I have questions.
Okay.
Again, how does a servo motor work with respect to computer control? Are you sending to it pulses? Are you sending to it a single instruction?
You're sending back pulses.
Okay.
And use a counter to count the pulses. And typical encoders have 5,000 counts per revolution. And so if you have 2,500 counts, you want to have it rep.
And are all servo motors 360-degree rotation?
I've dealt with that.
Okay. The answer is no. There's a whole plethora of hobby servos that only have a small range of motion, 60 to 90%.
Okay.
All right. Anything else? Nope.
Is there a benefit to that?
Having a limited range.
Yeah.
There are many mechanical devices that you don't want to run too far. And by having only a small range of motion, you can ensure that you're going to be in correct operating range for something.
Because I've always, like online, I've always seen like mods where you can fix these, make it a full.
There are some situations, and we'll see examples in little sumo robots or whatever, where you want the 360 like the one earlier. But in many cases, let's take an example, the flap of an airplane wing. You only want it to be up or down. You don't want it to rotate around and around and around, right? And so in cases where you only have a small little range, you actually can have, you don't need as much torque because it's only got a limited range and it could be smaller then. And that's the advantage of a limited range one, is they could be a lot smaller and a lot lighter. All right.
Traction control. The simplest way to explain what a traction is, it's usable, it's useful friction. That is, it's required for us when we walk, for the vehicles, for the wheels to rotate and stuff like that. Usable traction is dependent on the coefficient of traction, which is further dependent on the composition of the surface on which it is traveling, which changes as the vehicle moves over various terrain, which means that dynamically we need to control the traction during runtime. Now there are a number of these mechanisms which you can use to control traction. One is using brakes and the other one is using the engine power. So let's have a look at the first one.
Oh, an embedded YouTube video.
Okay, this is something, a video that I came up with. Here you can see that the power and the traction is equal for both of the wheels. And now here is an oil slick where you notice that due to reduced traction, the wheel spins faster. Now what happens is, in this case, the traction control kicks in. It introduces brakes, which reduces the speed of this particular wheel, and this again controls the speed of the wheels by which you can gain control over the vehicle. The second one in which you can control the engine power is the second one in which you can control traction is by controlling the engine power. Now this particular video, it goes more than 2 minutes, so you can have a look at it later. Basically what it does is it determines the speed of the wheels using a rotary sensors, and it controls the engine. That is, it is able to adjust the firing the firing pin of the 4-stroke engine motor. It's able to control the airflow and the fuel injection, by which you can reduce the power.
Three points off.
What?
Taking too long to get there.
Yeah, taking too long, man.
I'm John. I'm explaining propellers. As you can see up here, there's just two quick pictures of propellers, one marine and one aircraft. Propeller is a type of fan that converts the rotational motion of blades into thrust. As I stated earlier, the two main types are marine and aircraft. Some of the marine ones: controllable pitch, skew back, and modular. Controllable pitch, it controls the actual angle of the prop. Skew back is what you see in the picture when it's on larger ships or submarines, and it just brings the blades back a little bit so it grabs more thrust. And then modular is for more control, more speed, stuff like that, for like speed boats, bigger wakes, stuff like what you would need on a wakeboard boat or something. And then aircraft has a few more. You have fixed pitch, which is shown in this picture. It stays there all the time. It doesn't move or anything like that, so the angle never changes. You have in-flight adjustable, which obviously when you're flying you can change it. Ground adjustable, when you're on the ground, you can change the pitch. And then constant speed, it's an automatic pitch, so dealing with how fast the aircraft is going, it automatically changes its pitch to make it optimal. Questions? Oh.
My name is Tim O'Leary. I'm representing magnetic levitation. It's a long version for MAGLEV. It utilizes the attraction and repulsion of magnetic polarities. Definition of MAGLEV is a system of transportation that uses magnetic levitation to suspend, guide, and propel vehicles from magnets rather than using mechanical methods such as wheels, axles, and bearings. MAGLEV's been around for about 100 years. The idea was first thought of about 100 years ago by Emile Bachelet and Goddard in the United States. They never could find a practical way to achieve this goal. So it's been sort of, been in the works for a little while until about the 30s, until the Germans, they engineer everything. So Hermann Kampfer in Germany received a patent. He developed a way to use it in the transportation industry, but his work was disturbed by World War II, so sort of put a damper on things. In the 60s, the United States developed the first actual train, but they never put it into like the United States infrastructure. Then the Germans, in 1992, they created the first actual working transportation maglev train. It's very common nowadays in China and in Japan. There's two main types of maglev, EMS, which stands for electromagnetic suspension, and EDS, which stands for electrodynamic suspension. The highest recorded speed of a maglev train was 361 miles per hour, achieved by Japan in 2003. There's currently one in China that goes about 286 miles per hour. They have a 20-mile track. It goes from Shanghai to, let me see where it goes, to Pudong Airport. 20 miles takes them 8 minutes approximately. So normal standard high-speed trains travel about 186 miles per hour. So theirs is almost 100 miles an hour, more than that. So maglev trains, they do not rely on wheels, axles, or bearings. They're essentially frictionless, so this causes less maintenance on trains. Things tend to not wear down or break down due to friction and thermal occurrences. That's it.
Questions next.
I understand the linear motion on the screw. So a screw actually is a type of mechanical linear actuators that converts the rotary motions into linear. It's also convert the rotary torque into linear torque. The way it works is in the screw it has the helical thread that that allows the screw move back and forth. There are three different types. Well, there are different types of screw actuators. This screw, screw jet, bar screw, and roller screw. The picture on the top right is a design of a roller screw, I believe. And this picture right here is it's a linear actuator with this screw. And the screw actuator can be either manual, where you have a spindle and you spin it to move the screw back and forth, or it can be a electromechanical. So you have a motor that turns the screw around, you spin the wheel. So with this screw actuators, you have this screw, and then the tube that move back and forth, so you can attach whatever device you want to attach to it. And you also have the lead switches that prevent the screw go back and forth too far. So that can be your safety switches if you want to use it. And I also compiled a list of the different types of linear actuator types, and it's also a list of advantages and pros and cons of the different types of linear actuators. So depending on your applications or your environment, you can choose which one to fit your unit.
basically stands for mechanical electromechanical systems, microelectromechanical systems. Basically what that is electromechanical systems on the micro scale, so we're looking at 1 to 100 micrometers. Normally these aren't used, as we see right here, very small. They usually just have one CPU, a microprocessor, and like you see it's in the 1 centimeter down here. They're normally used in a combination effect, so it's not normally just one chip, it's only used in combinations, but it's used to control multiple different devices, and they're used in combinations to do anything from reading sensors, microsensors, and things like that, and then controlling it and activating other sensors. Examples would be printer inkjet, cartridges, things like that. Fluid pumps, you can use it pretty much anything on the micro scale. The biggest thing about this is that right now it's a $10 billion industry and it's ever growing. They estimate in the next 2 years it's going to be over $34 billion worth of industry. Basically because everything is getting smaller, as you can tell from iPhones to iPads to everything. The smaller, the more advanced. And that's pretty much everything that's about that.
So I want to talk about robotic leg that is powered by air, uses air for movement. This robotic leg uses pneumatic artificial muscles, also called PMS. The PMS can contract and extend depending on how much pressurized air is inside a pneumatic bladder or chamber. The PMS are lightweight, are easy to build, low cost, are very powerful. The movement is very smooth, are flexible, and they last forever. So they are very good actuators. This leg has 6 degrees of freedom. It has 2 on the hips, it has 2 at the ankle, it has 1 at the knee, and 1 on the toe. And every joint has a certain degree of movement. For instance, the one on the knee can move from 0 to 120 degrees. The control system uses potentiometers as a feedback to know what the position of the joints is, and to know the pressure inside the muscles. It uses an air delivery system that is inside the top level control system. This leg pretty much simulates a human leg, so it can move to any direction that the human leg does, and it has the same speed also. Last thing, he can also carry a load of 1 kilogram in each ankle while it's moving. This leg was made by Shadow Robot Company, and that's the website right there. They have videos there, and they have more pictures showing the different angles that it moves. That's a picture of the actual PMA. When the muscle contracts, raise the lever, and when it relaxes, just lower the level. And that's it.
My name is Herbert Hill, and I'm going to be doing a presentation on the Hall effect. The Hall effect was discovered by Edwin Hall while he was at the Johns Hopkins University in Baltimore, Maryland. And the Hall effect is basically the increase or decrease in voltage perpendicular to the path of current due to the presence of a magnetic field. And I have a video that kind of shows that in detail because it was hard for me to understand at first. Alright, so this video shows a current from a battery just going through a tube. The yellow dots represent electrons. And there's a magnet at the top that right now has no interaction, and there's a voltmeter. So as you move the magnet, and I'm going to show the field lines, as you move the magnet closer to the current, it changes the path of current, and it's kind of like when you have water going through a pipe, and when you disturb that, it causes pressure to build. And if you look at the voltmeter, the voltage changes as it gets closer or farther away. And also if you change the direction of the magnet, it changes the voltage. And also if you change the direction of the battery, which changes the current. And the Hall effect is used now in transducers and probes. So it's a way of, it can be used as a position control also. Are there any questions on that?
I'm Alex Monster, and I'm here to talk about the Gyroscope Technology. Gyroscope Technology is a device for measuring and or maintaining the orientation of a device. This is done with the principles of angular momentum. As you can see in the image there, the rotor is on the spinning axis, allows it to keep its position, the orientation of the gimbal, I believe it is. There are multiple kinds of gyroscopes. An easy form is a fast spinning mass which points in a fixed direction, which is what's shown in the image. An example of another gyroscope would be an attitude reference gyroscope used to sense or measure pitch, roll, and yaw of an aircraft. Uses of this can include compasses and computer point devices and more. I have a YouTube video here. It's an example of a form. This motorcycle uses
all the guts of it. So these are actually the gyros, power control, and batteries. So don't give that to our competitors. You have competitors? There's all.
That's all I wanted to show for now. Some other gyroscopes are the MEMS, Microelectromechanical system, FOGs, or fiber optic gyro, VSG, vibrating structure gyro, DTG, dynamical tuned gyro, and the London momentum gyro.
Alright, this presentation is on light detection and ranging, aka LIDAR. This is the use of light to detect distance away from an object. LIDAR is generally comprised of 4 parts, which is the laser. The laser usually operates within the 600 nanometers to 1 micrometer range, so that's near infrared, visible light, and ultraviolet. Another part of it is optics, so you have to have a mirror that bounces and deflects the lasers. Another part is the photosensor. This is located around the mirror, so when it bounces back, you can pick it up. And finally, you have the GPS, or an internal measurement unit. So if you take a look at the little GIF over there on the right, it's scanning the room and picking up all the objects in the circle. And if the whole rig was moving, you probably have a GPS in it. But if it's stationary, you probably wouldn't have any kind of measurement unit inside. There are a lot of applications for LIDAR. Stuff like seismic activity, or even farmers use it for determining if some land has good agricultural value. But for stuff like robotics, applications you can have are like topographical contour maps. So if you're a drone flying over, you can develop a map of the environment below. Threat detection, if you want military-based security or even home security. Automated transportation, same thing with vehicles or UAVs type stuff. And 3D point cloud to sort of determine objects. So if you have a robot, you can determine if a desk is a desk or a chair is a chair. There are a few examples, pictures. So the police LIDAR is pretty much, it sends pulses at your car, and it'll receive it and tell you how fast you're going. The Microsoft Connect, it has an array of infrared lights that shoot out at you and bounces back and then develops a 2D map of what's going on. And then the Navy Fire Scout, which is kind of the threat detection concept and the topographical contour mapping concept. And this thing is currently being used for hunting down like pirates in the ocean.
Arr, pirates, arr. All right, we're going to take a pause, so keep it right there for a second. I do want to debrief really quickly on what's covered so far, so some of you will be able to, unfortunately, recover a little bit. Hold on, I got to get this last set of scores. So far, most points have been off are because people didn't use the template. Remember, that was in the assignment. And some people used really funky stuff that I had to rework really hard. So again, for all the future ones, use the template. It's out there, plus then I'm assured that everything's going to be the right font, spacing, orientation. And you know, some people are talking and you know, they're just using. I sometimes am guilty of using the stall words, so watch out for that. Some of you need to be careful about your time. Most everybody has been between 1 and 2 minutes. Make sure that you are as accurate as possible. So what we will do right now is take a quick 5-minute break, and then we'll start back up. Go for it.
Alright, my name is Jessica Meeks. I'm going to talk about SONAR. SONAR was originally named after the anti-submarine division that invented it in Britain. But then the British shared it with the Americans and were like, well, let's name it something more descriptive. And we decided to name it after sound navigation and ranging. And it basically uses sound propagation to navigate, communicate with, or detect objects. And it's mostly used underwater, but it can be used different places. And it's used a lot in nature with like bats and dolphins and all those different animals. The two types of sonar typically used are active sonar, which basically you have a source sound that you're putting out there and listening for it to reflect back. And passive sonar, which uses sound that's already existent, like maybe from the motor of your boat or whatever it is, and receives that sound back to do the ranging and does basic reflective calculations that you would see in waves or whatever have you. And basic applications for this, it's used everywhere. Warfare was first because obviously submarine detection back in World War I was very important, and then now we've spread it to where we use it to navigate through such things as minefields if you have an automated missile or just regular deep sea devices, as well as scientifically they use it for mapping and getting the biomass of animals and that sort of thing. And along with that, you can use it for deep sea diving for civilian use, to look through coral reefs and see what's there, as well as just your regular fish finder that a lot of people probably have on their boats.
All right, I'm Benjamin Rose. I'm going to talk about accelerometers. What's an accelerometer? It's an instrument used for measuring acceleration and gravity-induced reactions. So anytime you research something, you want the 6 major things: the who, what, when, where, and why, and how, of course. So who invented it? It was George Atwood in 1783. Don't really recognize it, but it was a kind of a pendulum mass kind of system that used acceleration for it. What do they look like? Here's an example of a small IC package, typical accelerometer. They vary sometimes in packages and sizes, but that's the typical size. They're used for embedded systems, of course. When do we use one? Probably everyone in here has used one today. If you use your iPhone today to text with the on-screen keyboard and flipped over, it's using an accelerometer. If you have a Wii, your Wiimote has an accelerometer in it, 3-axis. Where can they be found? Well, anywhere from on your waist to outer space. So if you use a pedometer before, if you worry about your weight, they can use one of those. So they also use those in the space station, for frictional forces and things. And they also for, well, it used to be landing the space shuttle, but unfortunately they done away with that program. So when do we need them? We need them actually all the time for safety. If your airbag is deployed in a car, if you might have been in a car crash, you can think while you're alive to accelerometers. So, and lastly, how can we survive without them? You wouldn't have any planes, trains, or automobiles without accelerometers. And if anybody worries about what this picture is, this is a movie with Steve Martin and John Candy in it, or Uncle Buck, if I like to call him. If you hadn't watched the movie, do yourself a favor and watch a movie with accelerometers in it this weekend. So that's all I got.
The topic I chose was GPS, or Global Positioning System. And what this is a space-based satellite navigation system. So it works in any weather, which is slightly different than some satellite systems. But it must be visible by at least 4 satellites, and this is due to the 3 dimensions of Earth plus latitude and or longitude. And so it's free to access as long as you have a GPS receiver device. And the way it works is it receives signals from the different satellites, and it times each signal and able to triangulate your position in relation to the Earth. And the speed of the satellite orbit as well as the speed of light are both taken into account when calculating the point of the receiver device. And the user device that actually receives these signals never sends signals. It only receives the signals that are sent by the satellites and uses these signals to calculate its actual position on Earth.
My name is and I'm sharing the topic of temperature sensing, which is a technology used for measuring the temperature gradient of a substance or an object. The applications could be as simple as you checking the day temperature to choose an outfit for the day, or it could be as complicated as a chemist measuring the temperature of a substance to analyze the data of a chemical reaction. Now I'm sharing with you 4 examples today. On the top right, you can see a thermistor. A common example of that would be mercury in glass, where the expansion and contraction of the mercury volume in the glass determines the temperature. A second technology is a thermistor, which is a resistor that varies the resistance based on the temperature, where the temperature increase would decrease the resistance. It is made out of semiconductor materials. In contraction to the resistance temperature detector, which is also known as RTD, it's made out of metals. And the RTDs, as the temperature increase, the resistance increase. For the resistance, it's basically measured by applying a constant current and measuring the voltage drop across the resistors. And finally, a thermocouple, which is a device that has 2 conductors, and it measures the temperature, and it outputs a voltage value which is proportional to that temperature. And that's it. Thank you.
My name is Eric. I'm going to discuss touch sensing. Touch devices are devices which measure the parameters of contact between a sensor and an object. We have 2 different, it could be touch or tactile. Touch determines and measures the contact of a force on a single point, and tactile is a detection and measurement of a special distribution of a force on a coordinated group of touch sensors. Quantum tunneling composite is a technology in the touch sensing range or area, and it's more accurate than the resistive. How do you call it? It's more accurate than the resistive, and it takes less power than the capacitive. It takes less power than the capacitive since it draws current only when a force is applied to it. As you can see in the picture, for the graph, as the force is applied to it, the resistance lowers. So if less resistance, more current goes through it. This works on a three-dimensional interaction since you have to use pressure on it. It could let a robot, if it's used on a robot, it could let them know where it's being touched and with how much pressure it's being touched. And this could lead to robots that have better designing, grasping capabilities, and better interaction with humans.
Hi, I'm Trip Taylor. I also go by Patterson. I'm going to teach you about pressure sensing technologies. He just talked about one of them that can be used for 3D interaction with touch screens. But you have a couple different types of pressure sensors. You have absolute vacuum and gauge. And they tend, the absolute measures the absolute pressure. Vacuum measures pressure with reference to a vacuum, and gauge measures it with reference to atmospheric pressure. Then they typically take the form of a differential pressure sensor. So you have a diaphragm or a film and pressure on both sides of it. So what it's measuring is the difference between those two pressures to create a voltage or a current, which is then used to tell you the pressure difference. You have something like piezoelectric strain gauges. That was the type that we just saw up there. I believe that used a quartz crystal to tell when you push on it, it generates current, so you can tell how hard you're pushing on it. So that's one of the types. You can see you got your crystal in there, your pressure input, and then you get pressure sensing background of voltage difference. There's also electromagnetic and capacitive sensors that use differences in electrical or magnetic fields and currents, and they can create a capacitor with a vacuum also to operate in the same fashion, where it uses a diaphragm and different pressures on different sides of the diaphragm. And that's how most pressure sensors work, and they're used in a lot of different applications. My senior project, we're going to end up having them in our air muscles that you saw in the leg actuator using pneumatic muscles. We're going to have pressure sensors in each one of those so that you can tell exactly what the pressure is. Your barometer tells you air pressure outside. We use pressure sensors all the time, everywhere. Pressure sensors.
One topic was cameras and robots. Robots use cameras as a way to they take them in as input, what comes from the camera, and they do this with image recognition and depth sensing. And based on some of those inputs, the applications for that can be the response to human interaction, mapping an environment, you can navigate the environment, and they can also respond to certain images and objects that they see. And my favorite camera to use
is the Connect, just because for the price that it costs, it can actually do a lot of stuff. And there's a video that I've listed with it that I'm not going to look at, but if you're interested, you can look at it later. But some of the cool things that the Connect itself can do is, of course, the Xbox games that it comes with, but also people that use it in robots can use it to navigate terrains, also to scan barcodes, to look at people and recognize based on their profile and do different things. So cameras and robots have a lot of uses and a lot of different applications.
All right. So let's do a quick debrief of all of this and see what you think. I guess the first question is debrief. What did you think? Was it useful? Was it helpful? Was it just a painting? What do you think?
Good.
But it was good. How many of you were nervous as anything? Okay. And Ruba, I'll point you out because it sounded like your voice was wavering. Right. Now, considering that I think you went through the Leadership Academy, is that correct?
Yeah.
Why did you get so nervous?
I don't know. It's like hard when like someone, like, I don't know.
Okay.
When you're on camera and like, you know someone's grading you and I don't know.
Okay. Okay. Well, do engineers do presentations?
Yes.
All the time. In fact, one of the memes is my favorite. You know, the memes they put out there. The black background, they show pictures. You know, this is engineers. This is what my parents think I do. This is what my friends think I do. You know, this is what I really do, and it shows PowerPoint. All right. So. The whole idea is to get you involved. Yes, question?
Can I ask something that I'm working for a Reaper right now? And
you got to speak up, I can't hear you.
Yeah, I am working for a Reaper right now, and we have to do a lot of these stuff, and I am lacking that skill, so...
All right. So you're doing presentations all the time at work, and you just started, right?
Yeah.
So you don't have to be a manager, you don't have to be somebody, you're making presentations all the time. This is a specific style called micro presentations. And what I've often seen when I was in industry is that people would be asked to literally make a short little 5-minute presentation. Give me 2 slides on this problem, what we could do to talk about it, how we're going to solve it. Nobody wants to sit around and listen to a 2-hour dissertation on a problem because it's all about, let's get it done, let's get it done, let's get it done. So, we're going to do 3 more of these. If you want to, we could do a 5th one.
No.
Oh, yeah. 3 more plus 1, that's 4.
1 plus 4, yeah, okay. So let's take a vote just for grades. Who wants to do 4? Who wants to do total? 4 total. Who wants to do 5 total? And not everybody raised their hand. All right, let's start.
Who wants to do 3 total?
You got a choice. 4 or 5. Who wants to do 4?
What's the difference between doing 4 or 5? They count less?
No, same number.
Is this being replaced?
Well, how? Let's do 4. Don't you already have the scale? 4. There's a homework.
All right. There are 5 homework assignments in this class. Right now, only 4 of them are identified as presentations. The 5th is a paper one.
No,
So let's again. How many want to do 4? How many want to do 5? All right. Which is actually very nice because it gives you a little bit more practice. You will be asked to be better and better each time we do this. So some of you missed points on not using the template. I bet you that won't happen again, right? You'll give you a little bit of pain up front, and then you'll get better later. Nearly everybody was between 1 and 2 minutes. This next presentation, as I mentioned in class, will be right on a robot, or do a presentation on a robot. Specifically, identify, and I'll come up with the rubrics of what you have to present. But things like sensors, on this robot, actuators on this robot, and the important functionality of it. And
can I use the seal robot?
can you use the Pero seal? First come, first serve, because you're going to have to dissect that puppy. Well, I mean, you know, not really buy one and take it apart, but to actually identify what it is. All right. Yeah, the next thing I'm going to do is start talking about seal plumbing. So, what I wanted to do is to finish up our book on some concepts associated with locomotion. And, you know, our book does a pretty good job. It goes into some depths that I really am not wild about, but I want to at least bring up something about wheels. And so I have here a, let's see if this even powers on. Oh, let's see if it even has batteries. It has a battery, but I don't think that this battery is charged. In fact, I almost assure you that it's not charged. So what better way to take a look at a robot than to turn it over? And no, I am not going to be able to see the gender of this robot, all right? So this is another example of a commercial robot. No, this is not FDA approved. Does it need to be FDA approved? Probably not. Actually, there are some medicine delivery robots that run around in hospitals. It's basically a box on wheels. It either follows tracks in the floor, or it's pre-programmed to see openings and doors and things like that. That actually had to be FDA approved as well. Welcome to the world of government control. All right, so we have down here the bottom of the Roomba, which has wheels. If you look at this carefully, this has an interesting shock absorbers. But the other wheel here, and these are the only two wheels that move, but they also have something that is, oh, look at that, it doesn't turn or anything like that, right? So it'll go forward and it also absorbs, but notice it doesn't have any Swedish wheel type of thing up here. And when they went to a new version, they actually put on this a cast or a wheel that would actually move in different directions. But what other actuators do we have here?
Motor.
This is a cute little thing. When it's running, it goes along and sweeps stuff, and I think it rotates in this direction, so it sweeps stuff underneath so that it'll be sucked up by the vacuum. What you have here are brushes, or brushes, and there are motors here as well.
You can't see that part.
So right here are motor drives as well. To be able to turn the brushes, there's two different ones. There's this brush, which is rubber, this brush, which has bristles like you typically see. And they sweep the dirt into this cavity under here, and this cavity under here. This works a lot different than mine at home. The cavity under here fills up with crap, and here we go. And then you pull it off and you dump it. And it does have the capability for filtering air as well, at least the newer ones do. But it also has this sensor on top. What do you think that's for? It's a bump, yeah. So these things used to go full-fledged or full power right into the wall. And the newer versions came out that it actually would use a sensor on the front. They're not on these. That would detect when you're getting close to the wall and would slow down before you hit the wall. This is infrared that is actually used for communications to go to its charging station, as well as they have a technology called a virtual wall. So if I wanted to vacuum one room, let's say you have a house that has a living room but no door to it, and you want to only vacuum that one room, you could put up a small little lighthouse, they call them, and basically block off the entrance to that room so the robot would stay inside there. Let's see, what other do we have here? This, under here, you will not be able to see as well unless I zoom in. And I really can't tell too well. In here, which you can't see well, is an infrared light and sensor. What do you think that would be for?
Stairs.
Stairs. So it keeps you from going downstairs. So it looks for a cliff when you're going from half an inch, 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 6 inches, you know, really long. And it'll keep it from going forward. All right. What I wanted to show just briefly, and we're going to get into this in a lot more detail later, is the concept of intelligence when you're running a robot. So in this case, we have two devices. We have the iRobot Roomba and a Nito. I like the name of that, Nito.
This is neat.
The iRobot only, and this is the vacuum cleaner that I have at home. And my kids have named it, although I don't know what they've named it, they won't tell me. The device really only has very local sensors. However, this other vacuum over here, the Nito, has a rudimentary LIDAR. And so you just learned about what LIDAR was, right?
Yeah.
It can kind of use it to map out the room. Roomba can't map out a room because it doesn't have the right sensors. But the Nito can. And what it will do then is, in this case, what we have is a time-lapse photograph of this running as a Roomba. So you notice that it's very chaotic and random. It will go around the edges very well. By the way, right here, you probably can't see it that well, but right here is what's called a lighthouse. It's keeping the Roomba from going any further this way. And I believe this is a coffee table of some sort, yeah. And also notice that it goes around this leg right here, same way as this one does. But it's chaotic. It hits a wall, it turns at a certain degree angle, and then it'll go off. So like here, it probably hit the wall, turned around, and then came this way. Here it hit a wall, turned around, and went this way. Very chaotic. Are there any areas it really didn't get to clean? Well, this ran for a very long time.
Yeah.
There's some areas over here, maybe it didn't clean so well.
Yeah.
Now, contrast that with this device, which is a lot more methodical in how it's cleaning. I don't know how many of you actually use a vacuum cleaner by hand, all right? So when you do it, do you just start doing it over here, and then you start going over there, and then you go over there? You kind of do it in a row, and then you go to the next row, and then the next row. This is methodical. It's ensuring that it gets as much of it as possible. This is now something to think about. This is using wheels, this is using wheels, so that means it has very good control of its environment of where it's going to move. So what's the difference in this one versus this one with respect to control, localization, observation of where it is? What do you think?
The one on the right's a lot more efficient and faster.
All right. It's more efficient and faster. Do you think it would have more microprocessor power, brains, thought, algorithm, whatever?
Definitely.
So this is a bit more random. There's a...
Rather the Roomba.
There is a... pardon me?
That's a much more thorough job on the left.
Ah. Well, that's another thing to think about, too.
How much do those things cost?
Which one?
The nice one. Aren't they expensive? Like,
I'm not sure. Somebody has a computer open. You gonna look it up?
aren't they expensive? Like, wouldn't it just be?
By the way,
cheaper to get them
if
made?
you are a fan of Woot, Woot just had a couple of days ago, I think it was that actual Roomba was for sale for $160.
$340 for the Nito.
For the Nito.
Yeah.
And usually the Roomba is about that same price, but the Woot sale was a refurbished one, and it's not the top of the line, but it's pretty darn good.
The newest Roomba is 600.
Oh, yeah.
That's not the newest Roomba.
Yeah, I'd rather get a Dyson for that price. That's like 4 maid cleans.
Yeah, I'd rather get
And the maids do the countertops and the tubs and everything like that. Like,
yes, but that's only what?
one-time payment.
Once every 2 weeks?
Yeah, once every 2 weeks.
All right, so what are we going to do after 2 months? Bye, Duke.
You're probably going to end up buying a new one and putting those on the counters and stuff.
Well, think about this. Well, actually, they sell something called Scuba, which cleans kitchen floors. They actually sell a, this is iRobot, they sell Luge, who came up with that name, I don't know, that is, cleans out gutters. So they have all sorts of
gutters?
Cleans gutters.
No way.
Way.
Oh, I see way. That's impressive.
Yeah, that is pretty good.
All right, so wheels I'm not going to go much more into. And then finally, this is a general classification, this is in your book as well, of air vehicles. And if we look at all aircraft, we have ones that are lighter than air, basically that are held up because they're filled with, I fill them when I'm talking to my lecturers, right? Balloons, blimps. Believe it or not, there's blimps are making a comeback for robotics. Reason being, they can float. And they just sit there without very much energy needed to be expended. And they can actually carry quite a bit of payload. So they're finding interest. They have competitions for controlling a blimp. The other problem is it's very hard to control. And they're very susceptible to winds and stuff like that. So in heavier than air, we have non-motorized, which we don't really care about, but we worry about things like planes, rotorcrafts, and other bird-like devices. VTOL is vertical takeoff and landing. And what you will find for something like that is a quad rotor. So I'm doing research. Here, I should show this so that the whole world out there. I'm doing research in quad rotor. I had a student that actually did a project. The objective of the project was to land this on an oscillating surface. So if you can imagine an oscillating surface is going up and down, slowly, but going up and down. We want this to land on it. Now, what do you think would be an oscillating surface?
A boat.
A boat. So not only does a boat have transverse motion, but it also has pitch and roll as well. And so the objective was to, using that device, to match the pitch and roll of the boat and then slowly land on it without breaking anything. And he got pretty far. And I'm sure you've seen this one before. I bet you they brought down the one that actually has it in here.
That's probably it.
Here we go. The Parrot. So the Parrot is, it's still a toy. This thing is light. If you haven't seen one before. And it's really made cheaply. You could just come up and look at the difference in the motors on this one that spin really fast, and they're made of metal. And this, which is not so fast, and it's made of plastic, and it's a lot cheaper. You'll also notice that there are pieces that are coming off of this, and it's even taped up in the bottom with duct tape, so something else tells what's going on. It does have a camera on the front, and it will. This will transmit whatever it sees.
Yeah, so you iPhone.
Now, I have to now do one kind of confession with respect to this. I had one student that we bought one of these devices and he programmed it, and I told him that when you first test it, make sure you test it indoors to make sure the software is right. His testing was, turn it on, it turns, good enough, let's go outside. The software was not correct. It took off and stopped listening to the control panel. And kept going up and up and up
Is that what that
and up and up. And he's, pardon me?
Greg, I saw
That was the sign that said lost cross.
Yes. Have you seen me? My graduate student who did that was so docile after that he would do anything I told him to do. So.
Did you ever find it? Never found it?
We never found it. Well, in some cases I maybe not want to find it because you never know what it hit on the way down. Because eventually they have to come down.
How long is the battery life on that thing?
An hour.
An hour?
And so really depending on which way the airs blew, the winds blew that day, you really didn't know where it would have landed. It may be in the middle of Lake Norman. It may be in a pile of pieces in a parking lot somewhere. It may be in some kid's bedroom because he found it in the woods. Who knows? So I'm not going to worry about that.
How heavy is that thing?
How heavy is it?
Wasn't that something?
Catches the drift.
So,
I'm at like a poundage.
yeah, I would say it's about 2 pounds. I mean, this thing over here is probably a quarter of a pound. So, that's all I wanted to cover for today. We will continue with Chapter 3. How many of you do not have a book yet?
Shit.
All right. I will post chapters 1 through 3 if I can. And then, that's it. And by the way, there will probably be a quiz on Chapter 2. Thank you very much.